Swayam Prabha. Digital India. Educated India.
So, in last class, we have discussed about this inverting amplifier, right? And we have also, estimated the gain of this inverting amplifier, right? Okay, for our quick reference, let us do that part quickly here, okay? And then we will start our discussions for today's class. So, we were discussing about this inverting amplifier. And if you recall, then the circuit was like this. This R2 by R1, this is V output and this is V input, right? And we have estimated the gain from this. So what was the gain? Gain we have found, obviously this is a closed loop gain, right? Because this, you can see there is a negative feedback from this output to this input. It is connected with the this negative terminal or the inverting terminal of this op amp. And the gain, what we have estimated in the last class, it was R2 by R1, isn't it? Right. And during this estimation of this closed loop gain, what we have assumed that the differential open loop gain of this op amp is actually infinite, right? So we have assumed AOD, this is infinite, right? But actually it is not infinite, right? We have seen that in the last class, but it is a very high value, right? So let us see the effect of this AOD on the gain of this inverting amplifier, right? So here what we are assuming that this, for the time being, let us consider that this AOD is not infinite but AOD is finite. So we are considering this finite open loop gain, which is AOD. So if it is a finite open loop gain, then we have to cross check whether if we estimate the gain, then will it come out to be this R2 by R1, or how it will deviate from this estimated gain considered for an ideal op amp. Okay, so let us see that here. But before that, I think it will be good if we draw the equivalent circuit of this op amp, okay, for better understanding of yours, right? So here what we are considering, we are considering these two terminal of this op amps, right? And this is the output terminal, and we are considering that this op amp input resistance is still very high. Okay, that means no current is flowing to this op amp or coming out of this op amp. Fine. And you remember that the opened this circuit, right? We have also done this part. It was AOD into V2 minus V1, where this was V2 and this potential was V1. So this is that negative and this is the negative, means this is the inverting terminal, this is the non-inverting terminal, right? And like we can also see here, one resistance R1 was there. So let us say that this is that R1 and this is that R2, right? And this is the output voltage, right? And here you can see this terminal is grounded. So let us also ground this. And here the signal Vi or the DC voltage Vi is being applied. Fine. Okay. Now you can see that earlier we have assumed that the gain is infinite, right? So we can apply the virtual ground concept. That means V1 and V2 are in the same potential, but now we are saying that consider the gain of open loop gain of this op amp is finite, so we cannot apply the virtual ground concept, right? Remember that. So we are considering for the time being that this V1, this potential is V1 and this potential is V2, which is obviously ground, right? So what will be the current I1 which is flowing from this to this? So what will be this I1? I1 will be equal to this V in minus this V1, right, divided by this R1. And as again we are considering that this input resistance is op amp is infinite, so no current is flowing inside this op amp, right? So this I1 current has to flow through this R2, isn't it? Right? Okay. So that way, what would be the value of this V output from this? Or maybe let's say that this current is I2. Let us say where this I1 equal to I2. So we will do step by step. So what is this I2? I2 is nothing but this V1 minus V0 by R2, right? Okay. Then what is this V0? Output voltage. Then the output voltage is nothing but, you can see from here, this equivalent circuit diagram, it is V2 minus V1, right? What is this V2? V2 is 0, grounded, so it is minus of A of OD into V1, right? Now we know that this I1 equal to I2, right? So that way you can also write from this equation and this equation that this equal to V1 minus V0 by R2, isn't it? Right. So here we have to replace few terms, right? For example, how can we replace this V1 term here? See here, this equation, it is V1 is related with V output, right? So how can we write then V1? V1 is V output by A of OD, right? So let us write it here then. So it is this minus, then here also one negative sign is there, so it become plus. It's V of V0 by A of OD by this is R1, right? And here it is V1, so again replace it by this V output A of OD minus V output by R2, right? You can now just multiply and take V output one side and V input in the other side, right? If we do that, then what we will get is this V output by this V input. Okay, this will be equal to minus of R2 by R1 into 1 plus R2 by R1 into 1 by AOD. Fine. So you can please cross check it from here, right? You take everything V output one side and V input in other side, and then estimate this V output by V input, which is nothing but this is the closed loop gain, right, of this circuit, right? Okay. Now here few observations. First observation is, let us write it here. So first observation is, if AOD tends to infinity, see, if this AOD tends to infinity, right, then this part, right, this part become 0, isn't it? This entire part become 0, right? Then become gain become minus R2 by R1, which is exactly this one, isn't it? Okay. So if this, then this gain is equal to minus R2 by R1. And just to take type of, for our better understanding, let us assume here that this is R2 is 10 times of R1, right? So here in that case gain would be how much? Minus 10, right? For ideal case. So here also you can see the gain is coming out to be minus 10, right? Okay. But now let us consider some other value. For example, let us say that this AOD, okay, this AOD value is 100. So if you consider AOD value 100 here, and if you put this R2 by R1 as R2 by R1 as 10, okay, then if you calculate it, you will find that this gain will come out to be minus 9, right? You see, when the open loop gain, that is this one, is 100, then the gain is coming minus 9, but it is estimated, we have estimated from this ideal case it is minus 10, right? But it is lower than this gain. Okay, let us consider some other value. Let us say that AOD is 1000. So now if you calculate it again from here, you will find that this V gain, voltage gain, will come out to be 9.89. So now you can see it is much closer, right, to this minus 10. Okay. Now one more case. Suppose this you consider the gain to be 10 to the power 5, which is nothing but 1 lakh. That we have also seen in last class that the gain, open loop gain of this op amp is generally in the range of 1 lakh to maybe in the 1 lakh or even higher than that. So in that case, this gain, overall gain of the circuit will comes out to be 9.998. So you can see now it is very close to that of this ideal scenario. And this gain, open loop gain, is not difficult to achieve for this practical op amp. Okay, so then for practical op amp, you can use this virtual ground concept. Okay, but if in any problem explicitly it is mentioned that the gain is lower, or open loop gain of this op amp is lower, then you cannot use the virtual ground concept, right? But in all practical op amp cases, you can assume the virtual ground concept. Fine. Okay. So if this circuit is clear to you, then let us consider another type of inverting amplifier where we will modify a little bit about this R2. Okay, this place of this R2. Why we will do that? Because you can also assume from here. See, for example, let me pick another color. Yeah, this. So here you have seen the gain is minus R2 by R1, right? And suppose the R1 value is fixed at, suppose 10 kilo ohm, R1 value, fine. And what you need is this gain is to be 100, right? Then what should be the value of this R2? R2 should be 100 times than that of this R1, right? So that way it will become 1 mega ohm, the value of R2, and you can see that this resistance is quite high, right? So if you want to use this non-inverting amplifier to amplify a particular signal of 100 times, right, then it is quite difficult to implement that, right? Because then you have to use some resistor whose value is very high, right? And for any integrated circuit, implementing a very high value of resistance is quite difficult, right? So that is one aspect from this which we can solve in the next circuit. Let us see how. So here we are considering an inverting amplifier with T network. So it is inverting amplifier with T network. So what are we doing here? This is grounded as earlier, right? And we have a resistor here, R1. We have applied the input here. This here we will do the modification. Here we use a T network. This is R1. This is, let us say that this R2. This is R3, and let us say this is R4. This is V output, right? And this is grounded. This is ideal op amp. This is ground, virtual ground concept. So this potential is also at 0 volt, right? Fine. Okay. Now let's see about the current. Let us say that this current is I1, right? Then the same current has to flow. No current will flow inside this op amp. So the I1 is flowing through this, but we are taking this current as I2, right? So this potential is 0, current is flowing like this, so this become positive, this become negative, right? So if you assume the potential here is Vx, then obviously the Vx potential will be negative, right? Now this is at ground potential, 0 potential, this is negative, so the one current will flow through this R4, which will be in this direction. So let us say that this is I4, right? Now these two current will combine from here at this node and will come here, right? And let us say that this current is I3. Fine. So remember, here we are considering the ideal op amp where the open loop gain is infinite, and that's how we have used the virtual ground concept, and we have seen that this potential is at 0, right? Okay. Then what will be this I1? I1 is nothing but V1 by R1, right? And this is same as this I2. Okay. Then tell me what will be the value of this Vx? Vx is nothing but minus I2 R2, isn't it? So what is this I2? I2 is Vi by R1, right? So it is minus Vi into R2 by R1, isn't it? Okay. Then what is this I4 current? What is this I4? So see here, 0 minus Vx by R4, 0 minus Vx by R4, right? So what is this Vx? You can put it here, right? In terms of this, this Vi, if you want to replace it. So here it will become Vi. So will it be minus? No, because the 1 minus it is gone. So it is R2 by R1 R4, right? So this is the value of this I4, right? Now what is then I3? I3 is nothing but I2 plus I4. I3 is equal to I2 plus I4, right? Then how can we represent this I3? I can write I3 like this. It is Vx minus V0 by R3, right? What is this I2? I2 we have already found in terms of Vi. It is Vi by R1, right? What is I4? I4 also we have estimated here, which is Vi into R2 by R1 R4, isn't it? Okay. Now you see here there is one term, this Vx. Now Vx we have to replace with this. Vx is equal to Vi into minus of Vi into R2 by R1. So replace that here. Okay. So if you replace it here, okay. Now put Vx equal to minus Vi into R2 by R1. Then you can see this, in this equation you have a relation between V output and V input, right? Other than that, everything will be in terms of this resistances, right? These 4 resistances, right? Now after that, if you take all this V out in one side, right, and then you will find that this V output will be coming like this. V output equal to V input into R2 by R1 here, 1 plus R3 by R2 plus R3 by R4, right? Then if you have to estimate the gain, then this gain would be equal to V output by V input. This is minus, this is R2 by R1, this is 1 plus R3 by R2 plus, right? So you can see here the gain for this type of non-inverting amplifier, where we have changed the feedback path by this T network, then the gain is becoming minus R2 by R1 into this. So if you have to take, suppose make the gain 100, then it is not only now dependent on this R2 by R1, but the multiplication of this with this factor, right? So here the individual resistances, the value of individual resistances, you can control quite easily, right, compared to the previous non-inverting amplifier case, simple non-inverting amplifier case, right? And as it is a inverting amplifier, so you can clearly see the negative sign here, and that is also expected, right? Okay, then I hope this inverting amplifier with T network is clear to you, right? So in that case we can proceed and do the next part, which is the another amplifier, inverting amplifier only, but there we don't have a single input, but we have multiple inputs. Okay, means multiple either DC voltages or maybe some multiple AC sources. For example, let us see the circuit here. So we have this op amp, negative, positive, right? This is the inverting terminal, non-inverting terminal. Non-inverting is again grounded, and we have in the feedback loop we have only one resistor, like simple simple inverting amplifier case. This is RF. We are denoting it as here RF because it is a feedback resistor, right? And here we have multiple inputs, and multiple inputs are connected like this. This is R1, this is R2, this is R3. You can have even more, right? You can have even more. So, and here this supply voltages are, input is V1, this is V2, and this is V3. These are the three input three input voltages, and R1, R2, R3, right? And this is ground. So in that case, can you find what will be the output voltage? How to approach? You have multiple input voltages, right, or input multiple sources, right, connected with that. So in that case I think we can use the superposition theorem, right, so that we can estimate the output for one input to be applied, while you have to ground the other, or zero, make the voltage sources apply to the other terminal as ground, right? And you can analyze what is the output for a single voltage source, right? And then you can estimate for the second, third, and whatever, and finally you can find what is the total output voltage by taking an algebraic sum of all these individual outputs, right? So we can apply the superposition here. Fine. Okay, so in that case tell me what will be the value of this I1 here. Yeah, what will be the value of this I1 here? So definitely this is grounded, ideal op amp, virtual ground concept. So this is also at zero potential, right? Now when you are considering superposition theorem, when we are considering for V1, Okay, V1 is applied. When only V1 is applied, then V2 is grounded, this V3 is grounded. So this is grounded, this is grounded. So now you can see here, this potential is at ground, this potential is also at ground. So this I1 cannot flow to this R through R2 or R3. So whatever I1 is flowing, that has to now flow through this RF only, right? Okay, then in that case, what is the value of this I1? I1 is nothing but V1, let us say this V1 by R1, right? Okay, then what is the value of this V output in that case? V output is nothing but, if this is I1, it is minus of I1 into RF. Why minus? Because current is flowing here, so it is plus, it is minus, so V output would be minus because this is grounded, right? So in that case, what will be the V output? You just substitute it here, so it will be this V output into RF by R1. So this is the V output, and let us say that this is the V output for when V1 is applied. So let us denote it as V output 1. Okay, V output 1 is this one, right? Okay, now then say when this V2 is, when V2 is applied. So when V2 is applied, what will happen? So when V2 is applied, similarly you can do what is, find what is the value of this I2, right? And then this I2 has to flow from here. Then you can also find what is the value of this VO2. So in that case, if you do that, you will find that this VO2 is this into RF by R2. Fine. Okay. Then the other case, when this V3 is applied, then you can also estimate what is I3, and that same I3 will flow through this, right? So when V3 is applied, right, in that case you can estimate what is VO3, which will be estimated in this similar way, and it will come out to be this one, RF by R3, right? Okay, I think one thing we have to correct it here. See, when you are considering VO3, the input is V3. So we should write here V3 specifically, right? So this is V3. Similarly, for this one, right? When this V2 is applied, so the input is this V2, right? Then here this input we should write this V2, right? Then what is the total output? If we have to then find the total output, then you have to take the algebraic sum of all three, this V01, V02, V03, right? Then what is the total output? Total output is V01, V02, V03, right? Now if you add all this stuff, you will be getting, so that way I think this will be also V1, right? This will be also V1, right? Yeah. So it is V1 into RF by R1, then minus V2 into RF by R1, sorry, R2, minus V3 into RF by R3, right? This is the total output. So this is basically V naught, right? So you can see then the total output in this case it will be like this. So here you can clearly see this output voltage is the sum of this V1, V2 and V3, because you can take this negative sign common and do that. Maybe it will be easier for you to understand if you consider the on a special case when this R1 equal to R2 equal to R3 equal to R, right? If this R1, R2, R3 they are of the same value and of R, right, in that case the output voltage is can be written as this one into this you can take then RF by R as common, right? So RF by R into V1, V2 plus V3, isn't it? V output is minus of Rf by R into V1 plus V2 plus V3, right? This negative sign is there, which is definitely is expected because it is an inverting amplifier. As you can see, this all three signals has been applied to this inverting terminal of this op amp, right? Okay, but if you see here inside, so you can see the output voltage is equal to the summation of this V1 plus V2 plus V3, right? Summation of all three input voltages. If you consider this V4, V5, then those terms will also come as a summation. So basically this particular circuit is doing what? It is basically summing up all these input voltages, right? So this particular circuit is called, or is also called, the summing amplifier. Fine. Okay, I hope this part is clear to you. Okay, so in that case, let us take after that one more example where we will not apply the signal to this inverting terminal, because so far what we are applying the signals at this inverting terminal, but we will apply the signal to this non-inverting terminal, and let us see then what happens, how the calculation or the gain of this particular circuit will change. Let us do that in the next page. So here let us consider this almost similar to whatever we have done for simple inverting amplifier case, right? So this is the output V out. We had for inverting amplifier case, we had an resistance R1 here, and we had a resistance R2 was there, right? And in the feedback, right? And this part was grounded, right? But here now we are applying the signal to this terminal only. So we are applying the signal here Vi to this non-inverting terminal, right? And this terminal, this R1, okay, where we have used to use the signal there, this terminal we are now ground, making that ground, right? Okay, again this amplifier is an ideal amplifier, so uh, this potential and this potential would be same. You remember virtual short concept. Why it is called virtual short? Virtual short because these two potential will be always equal, right? But there is no direct connection, so no current can flow between these two terminals. So they are actually short but virtually, right? So due to, it's called this virtual short concept, right? It is similar to that of this virtual ground concept that we have discussed earlier, right? So due to this virtual short, you can, this potential and this potential will be same, right? And that makes our analysis quite easy actually. So if this is then Vi, then obviously you can say that this potential is also Vi, right? Then this is ground, this is Vi, and say that one current due to this Vi is flowing like this, then and also let's say another current is flowing like this, and this is the ideal op amp, so no current is going inside to this op amp, right? Neither from this terminal or not from this terminal, right? Okay, so in that case, what will be the value of this I1? Okay, this current is nothing but this Vi by R1, right? What would be the value of this current, right, in terms of this Vi and this V output? It is nothing but Vi minus V output by R2, right? So, and again, if you apply one KCL at this node, then you can see this I1 plus I2, that is equal to 0, okay, right? So that means this equation, right? So you can now just directly put the values here, easy only, right? So it is minus of Vi minus V naught by R2, right? Now if you actually just do a the separation of this V output and V input, right? And take it in all this V output one side while V input in the other side, and then take this V output by V input. You will get it like this: R1 by R2 by R1, right? Which is nothing but 1 plus R2 by R1. So see this gain, this closed loop gain for this amplifier, where the signal has been applied to this non-inverting terminal. Here, as the signal has been applied to the non-inverting terminal, you can see there is no negative sign. That is expected, right? Because this output will be in the same phase of this input, right? Yeah. And what about the magnitude of this gain? You remember earlier for the same configuration for inverting amplifier, the magnitude of the gain was R2 by R1. But see, now the gain is 1 plus R2 by R1, right? And from this, obviously, you can say what is the minimum gain of this circuit. But if this R2 is even very very small compared to R1, even then the gain can be the minimum value of gain can be 1 only, right? Or you can say the gain is always greater than the unity for this type of non-inverting amplifier circuit, right? Whereas for inverting amplifier, gain can be even lower than 1 if you choose this R2 and R1 in that way, the previous case, right? Okay, one more thing is that what is the input impedance for this particular circuit? So input impedance means where you have input given the signal as an input. So this is this terminal, right? So if you look from here, that means to this, right? Then what you can see that this is the terminal or the input terminal of one op amp, and as this is an ideal op amp we have considered, so the input resistance, right, that will be also infinity for this case, right? So you can see then we are getting an signal which is been amplified compared to that of this input, right? And this type of amplifier where the signal has been applied to the non-inverting terminal is called the non-inverting amplifier. Maybe let me write it here: non-inverting amplifier, right? So here we can see this gain is always greater than 1, right? Okay, is this clear to you? Fine. Okay, if this part is clear to you, then let me ask one more question to you. Suppose you make the value of this R1 very 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 high, suppose infinite. Then this R1 is very high, say infinite. Then what will be the gain? Then the gain will become this part becomes 0, right? Something by infinity. So the gain will be nearly equal to 1, right? Then tell me, in that case, whether the gain is dependent on the value of this R2? No, right? If this R2 is finite, right, then the gain of this circuit, if this R1 is actually infinite, right, then the gain is independent of this R2, and gain is always nearly equal to 1. That means what I am saying is that consider this circuit where you have applied the signal to this non-inverting terminal. You have taken the output from here, right, and this is the inverting terminal, right? Earlier we have this R1 here, right, and this part was grounded, right? This was grounded here, right? But now what? And we have an resistance here, right? Let me draw this, then it will be easier for me to explain, right? And we have an R2 here, and this is the output voltage, right? But now what I am asking, and in that case, previous case, let me draw that, tell that as well. It was gain is 1 plus R2 by R1, isn't it? Now what am I saying? Suppose R1 is very high. So R1 very high means we can consider this R1 is not there, right? So the circuit is like this. So if this R1 is infinite, okay, very high, then if this R2 is finite, okay, maybe some kilo ohms, right? Then if the gain is becoming 1, right? It really does not depend on the value of this R2, right? So if this R2 value is equal to 0 also, then also the gain will become this equal to 1 only. So that means if we now just remove this R2 and just make this short, then also the gain will become equal to 1, right? So for this particular circuit, what you can see is that this output is following exactly the input, right? Output is following the input. So as this output is following the input, this particular circuit is called voltage follower. Fine. This is called voltage follower. Fine. Okay. So it is a voltage follower, gain is equal to 1. Then you might think, then why are we using this circuit? Because gain is equal to 1, we are not getting any gain, right? Then what is the advantage of using this circuit? The advantage of using this circuit is that it helps us in achieving the impedance transfer. For example, see here, last page only we have seen. If you see from here, what is the input impedance here? Input impedance is the input impedance of this ideal op amp, which is infinite, right? And if you see from here, this output impedance is 0, right? So this voltage follower can be used as a impedance transformer or buffer, right? So this is the primary use of this voltage follower circuit, that it can be used as a buffer or impedance transformer. Why? Because you know the input impedance is very high, the output impedance is very low. Let me give one example to you in the next page, then I think it will be much more clear to you. Yeah, so let us assume that we have a signal source which is this Vi, right? And the signal source has its own resistance, right? It's always have. And let us say that resistance of this source is 1 kilo ohm, right? And so this is the total part is the signal source part, right? And suppose this is actually driving one load resistance, okay, whose value is also 1 kilo ohm, right? So basically you are taking the output from here, from this V input, right? And what we have said is that this total part is the source, signal source part. This is the source part, right? And it is driving this load 1 kilo ohm, right? Then tell me, what is the output voltage here? The output voltage for this case would be definitely equal to 1 by 1 plus 1, just simple voltage division, right, into V in, right? So it is basically then V in by 2. So the output voltage is this input voltage by 2. That means if this signal source has a good amount of resistance, then that not the total entire voltage or the entire input voltage is falling across the load, right? But some part of the voltage is falling across this load. Got my point? But what we want is that the total part of the signal, if it is falling across this load, then you can use the entire signal. But here you are not able to do that. But suppose if we let us modify this circuit little bit here, and let us say the same source we are using, this plus minus, and this is V in. Okay, here now we have added one buffer, negative, this is positive, and how can you make a buffer? You have to just take it, right? This is the circuit that we have discussed in the last page, right? And this is the resistance, say load resistance, this is RL, huh? So this RL is 1 kilo ohm, and here it is this V out, right? So what is the input impedance here? Infinite. So the total V in will be falling. Okay, let us I forgot to draw this part, so maybe let me draw this 1 kilo ohm resistance as well here. So this is 1 kilo ohm, right? But what is the input impedance? If you look from here, this is very high, infinity, right? So that way, the drop across this 1 kilo ohm resistance, in that case you can neglect. You can assume that the total entire V in, or total entire V in is actually coming across here. Or in the other way also, you can think that as this no current can flow inside or out of this op amp, so no current is flowing, so no drop across here, so the entire V in is falling here, right? So if the entire V in is falling here, and what is the gain of this buffer? 1. So if this V in is here 1, what will be the output voltage in case of this particular circuit? So in case of this particular circuit, this output voltage will be exactly equal to this input voltage, right? So there will be no drop across this signal source, right? Almost no drop, right? So in this, so this is the use, okay, of this buffer circuit. Fine. So even though the gain of this buffer is actually 1 in the here, right? But this buffer can be used as a this impedance trans this for as a impedance transformer, right? And you can actually use this type of, if you have to separate this side and this side, right, isolate this two side, then you can use it, right? So I hope then this part is clear to you till this voltage follower part. So maybe in the next class we will discuss much more other circuits using op amps, right, which consist of this op amp as an integrator, differentiator, precision half wave rectifier, log amplifier, and then the difference amplifier. Okay, all this stuff, right? Okay then, thank you.